Right. So, previous class we have seen some graph theoretical concepts, specifically the Euler graph and how an Euler graph is useful in solving Chinese postman problem, and an Hamiltonian circuit is the answer for a travelling salesman problem. Now, we move ahead and some other important concepts, particularly the operations on a graph and tree and spanning tree. So, these concepts we shall discuss in this particular class. So, to begin with the operations, when we talk about the graph theoretic thing, there are several operations that we can do on graph. The very first two operations are usual, the union and intersection operation, right. So, supposing we have two graphs and there is maybe some common portion, then what is the union? So, the union of the graph, suppose I have union of graphs. Let us say we have two graphs here, one is this one and another is this one, right. So, these are the two graphs. Now, in these two graphs, let us see, suppose this is a vertex V1, this is vertex V2, this is vertex V3, and here we have V1, V3 and V4, and these are the edges E1, E2, E3, E3, sorry, E3, E4, E5. So, if you look at these two graphs G1 and G2, right, then in these two graphs there are some common vertices and there are one common edge called E3, right. So, if I have the resulting graph G, which is an union of G1 and G2, then what we should do? Then we know that we have to add G1, add G2 and minus the intersecting portion. So, if you add them, you know what will happen, there is V1, V3 and E3, they will come twice, because the common portion will come from both the graphs. So, you have to retain only one set and you have to forget the other set. So, what will be the union? The union would be simply, let us draw here, this is this one, then this one, then this one and then this one. So, this is our V1, V2, V3, V4, E1 and E2, E3, E4 and E5. So, this is the resulting graph G by which we have carried out the union operation. Similarly, the intersection of graphs can be also carried out by a process, that is G equal to G1 intersection of G2. What is that intersection? This intersection will be nothing but the common portion. So, tell me what is the common portion? The common portion would be the, your this portion, that this line only. So, this will be G, that is V1, V3 and E3. So, in this case the G would be like this. So, this side is union, this side is intersection. So, what happens that if you only look at the common portion, that can be called as the intersection of graph. So, these are simple concepts about union and intersection. Only thing that this union operator will apply both for vertices and edges, and intersection operator will also operate both for vertices and edges. Now comes a very important graph theoretic operation which can be called ring sum. Very interesting operation that is called ring sum. So, let us look at the same graphs once again, right. So, we have taken these two graphs. So, one is your let us put it here. So, this is what the graph we had. So, V1, V2, V3, V1, V3 and V4. This is E1, E2, E3, E3, E5 and E4. So, we have these two graphs, that is V1, V2, V3 and V1, V3, V4. So, let us call these as G1 and this one as G2. So, these are the two graphs G1 and G2. Now, the ring sum operation is G equal to G1, you see that plus and then circle, that is the ring sum symbol, G1 ring sum G2. So, you see this is very interesting, this is union G1 union G2 minus G1 intersection G2, right. So, both the union and intersection operation that we just now learnt both are required. So, one portion you make the union and the other portion we do the intersection and take out the intersecting portion from the union. So, what is the union? The union of these two graphs is this that we have already seen. This is the union. What is the union? V1, V2, V3 and V4. Then E1, E2, E3, E4 and E5, right. So, this is the union. And what is intersection? Intersection is only this much. So, if you take out from the union the intersection portion, then what will remain? What will remain is very interesting, is the ring sum. So, G1 intersection G2 would be nothing but this one. So, that is what we can have. In this case, if you look at this intersection portion, then the intersection portion graph would be that V1, V2, V3, V4, right. So, one thing to remember here, that the common edge is taken out, the common edge is taken out, but the vertices should remain, right. The vertices should remain, but the common edge should go out. So, that is what we do in the ring sum operation, that the common edge is taken out, but the vertices are taken. So, what is the advantage? The advantage is, suppose look here, if this is one circuit and this is another circuit, right. Supposing we start with this graph, let us say we start with this graph, and then you are told that how many circuits are there in this particular graph, right. So, you can say that this is one circuit and this is another circuit, but there is a third circuit also, that is the bigger one, is it not? These are the three circuits. So, if you have these two circuits and you do a ring sum, then you get a third circuit. So, that is what is the ring sum operation helps us, that if we have these two circuits, and you can find out basically with the help of ring sum the third circuit also. So, these particular specific advantage that the ring sum operation gives, that we shall make use of later as you proceed. So, we move on and then see another concept which is called the decomposition. The G is said to be decomposed into G1 and G2 if G equal to G1 union G2 and G1 intersection G2 is a null graph, right. So, the intersection should be a null graph, means nothing. That means that graph is completely these two has got no intersection, that is called a true decomposition, right. So, that is what happens, that if the intersection is a null graph, then we call that as a decomposition process. Now, look here, two more very important concepts. One is called the deletion of a vertex and a deletion of an edge. Please remember, if you delete an edge, the vertices that are connecting those two edges, the two vertices that the edge connects, they will not be deleted. So, if you delete an edge, only the edge is gone, vertex is intact. But if you delete a vertex, then all edge that is incident on that vertex, that is gone. Is it all right? So, one should remember these very carefully about it. Say for example, some student records, right. Here student is like a vertex, and these individual different subjects that the student has taken, that student to subject connections, you may call them as edges. Is it all right? So, if you delete a particular subject that student has taken, then that student subject link will be deleted only. So, that is like an edge deletion. But if you delete the student, then all subjects taken by that particular student are not the subject is deleted, that student subject link, all the student subject links will be deleted, right. So, must remember this, and that is what is done for the deletion operation. A particular type of thing is another one, that is called a fusion. What happens? Two vertices can be fused. So, suppose I draw a graph. For simplicity, I am not drawing the edges, I am not naming the edges. So, suppose this is a graph V1, V2, V3 and V4. Now, V1 and V2 are fused, right. So, V1 and V2 are fused to say V1 dash. So, V1 dash is the new vertex. So, how this fusion operation would look like? So, from this graph what we shall get is this one. So, you see V1 and V2 will be replaced by the new vertex V1 dash, and all the edges that were earlier connected to either V1 or V2 will now be connected to this new vertex. So, this is V4 and this is V3. So, these connections will remain. Now, you see this edge will be this and this edge will be this, and this one remain anyway as it is. But what will happen to this particular edge which was there? Suppose we call it E1, E2, E3 and E4. So, this is E2 now, this is E4 and this is E3. What will happen to E1? E1 will now become a self loop. So, this is called the fusion operation, right. So, you can fuse a particular two vertices, and as you fuse, the resulting graph could be like this. So, this is about deletion and fusion operation. Now, connected and disconnected graphs. So, in a connected graph there exists at least one path between two vertices, right. So, if you look at this graph G3, look at this graph G3. Can you find a path between A and C? No, answer is no. So, if there is at least one path, so if there is no path between A and C, obviously you have a path between A to E, but for every two vertices, between any two vertices, if you have a path, then you call this as a connected graph, right. So, disconnected graph is a graph where such a path is not available. So, this is a connected graph, this is a connected graph, this is not, because there is no path here between every pair of vertices. So, this is a disconnected graph, and in disconnected graph has got connected components. So, here you may call this as a component and this as another component. So, that is the basic idea about the connected graph and the disconnected graph. So, this brings us to a concept called tree. First of all, what is a tree? A tree is a graph without any circuit, right. That is the definition of a tree. So, a tree is a graph without any circuit. So, suppose I draw something like this, or suppose I draw something like this, right, or I draw something like this, right. So, G1, G2, G3, right. Now, we can also draw something like this, G4. Now, tell me, out of these four things that I have drawn, G1, G2, G3 and G4, are all of them trees? Are all of them having circuits? Answer is, here in G1 there is no circuit, in G2 also there is no circuit, G3 no circuit, and G4 however is not a tree because there is a circuit, right. So, this is how you look at the tree, but sometimes we can also define tree in a very simple way. A minimally connected graph is a tree. A minimally connected graph is a tree. So, you see, suppose we have this V1, V2, V3, V4, 4 vertices. And we want to minimally connect them, right. So, how many vertices? Let us say n vertices. How many edges do I require to minimally connect them? We need n minus 1 edges to minimally connect them, so that the resulting graph is a connected graph and not a disconnected graph. Because you see, suppose we connect V1 to V2, so one connection is gone. Now, you connect V1 to V4, so you see two connections are gone. Now, the third connection, suppose you use between V2 and V4, then you have already utilized your n minus 1 connections, alright, and but then you get a disconnected graph. V3 is not connected. So, you have to minimally connect that 4 vertices. So, you have no option by choosing the V2 to V3 or V1 to V3. You can choose any one of them. Suppose we choose V4 to V3. Suppose we choose, then we get a tree. So, that is a minimally connected graph. So, a tree is also a minimally connected graph, is a tree, right. In fact, you can also put this in another way. a connected graph with n vertices and n minus 1 edges is a tree. So, this is also another way you can define, because as long as you have only n minus 1 edges with n minus 1 vertices, it has no option but to become a tree, because it becomes minimally connected, and because it is minimally connected there cannot be any circuit. So, the base definition is always a tree is a graph without any circuit, but alternate definitions could be a minimally connected graph is a tree and a connected graph with n vertices and n minus 1 edges is a tree. Another way you can say, in a tree there is only one path between any pair of vertices. Look at V1 to V3, there is only one path, V1 to V4 only one path. Now, the question is that what is the significance of tree? You see, assume a particular graph, assume a particular graph Suppose let us assume this particular graph, or maybe if you want to make it slightly more complicated, then we can also take this. So, let us call it a graph. So, V1, V2, V3, V4 and V5. See, assume these are cities, V1, V2, V3, V4 and V5 are cities, right, and then you want to minimally connect them, right. How to connect these 5 cities minimally? You see, this graph represents possible road connections. These roads are not actually there, these are the roads that could have been built, but our budget is limited and we must give the minimal connectivity, so that any person in any of these cities can go to any other city, there is a path available. So, how to do that, how to minimally connect them? That is an interesting question, we will come back to that question little later. Now, look at this, there is another type of tree that is called a binary tree. So, what is the difference between a binary tree and a other tree? That in a binary tree is a tree definitely, but there is exactly one vertex of degree 2 and others are either one, like see this vertex which is a pendant vertex has got only 1 degree or degree 3, right, and number of vertices in a binary tree is an odd. So, actually there are a lot of applications of binary tree, particularly in the search algorithms and many such situations, but however we are mainly interested in the flow problems. So, we are not too much concerned about binary tree, and we will proceed further and see other type of important applications of tree. So, that is called what is known as a spanning tree. A spanning tree is is a subgraph of a connected graph G, and it contains all the vertices of G, but it is a tree. That's the essential idea. So, look here, in this particular graph there are 1, 2, 3, 4, 5 vertices, and these edges, if you take 4 edges, because there are 5 vertices, we can take 4 edges. If you take these 4 edges, then that forms a spanning tree, right. So, that is the essential idea of a spanning tree. Now, come back to the question that I have asked. Let us see whether an answer is found to this particular question. What was my question? That the graph shows possible road connections V1, V2, V3, V4, V5, they are cities, and the question was how to connect these 5 cities minimally, right. So, we need to build the least number of roads. So, how many roads will you build out of these 5 cities? You see, we discussed that if the number of vertices are n, then to minimally connect them we require n minus 1 edges. So, since there are 5 roads, 5 cities to connect, minimally we had to connect only 4 roads. Now, question is which 4 roads? That is a very important question. Which 4 roads? Which 4 road, that question we shall deal a little later, because each road has a length or a particular distance. Now, obviously we would like to minimize on the road length also. So, that is a bigger question, but initially let us only look at that what are the possible minimal connections. So, one such minimal connection would be that choose 4 roads. So, which 4 road we should choose? Let us start with, say, let us connect V1 to V2. So, this could be one road. Then maybe another 3 roads we have to choose. So, let us also take another road, say V2 to V3. So, 2 roads are chosen, right. So, make them double line, right. 2 roads are chosen. Then perhaps you take V4 and V5. So, this is another road is taken, right. So, you see these are the 3 roads chosen. Now, you have only one road to connect. Now, obviously look here, you can take which roads you cannot take. Let us look at, can I take this road? Answer is no, it cannot be taken, because then it forms circuit and then they are not connected. Can I choose any of the remaining 5 nodes, 5 edges? Answer is yes. We can take this one, 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 and we can take this one also, right. So, supposing we check this one. Okay. So, this is what we have got, what is known as a spanning tree. Okay. Because this is a particular, why? Because it has got, there are 5 nodes and we have got 5 minus 1 equal to 4 edges, and it is a connected graph. So, a connected graph, n nodes or vertices and n minus 1 edges. So, n nodes, n minus 1 edges, connected graph. So, it is a tree. So, it is a tree and it is a spanning tree because it spans all the vertices. But is it the only spanning tree? Answer is no. There are other spanning trees also. What are the other spanning trees? If I would have taken this, then another. If I would have taken this, another. If I would have taken this, another. if I would have taken this another instead of this. So, we could have got many other spanning trees. So, first of all, why these two? We could have chosen these and these also. So, like this, lot of options, a large number of selections of spanning trees are particularly possible. In fact, spanning tree is a very important concept, and we shall continue our discussions on spanning trees further, right. So, stop here for today. Thank you very much.